Hey, this is Chemistry Chapter 9, Lecture 2. You will need your lecture notes. We're starting at the top of page 4, your periodic table, and open your book to page 297. All right, so we're going to start with the on-your-own problems and draw these molecular shapes. Our first one is O2. So O2... Of course, each oxygen in column 6 has 6 valence electrons. All right, so we have drawn this several times, but you have a double bond with oxygen. And that is just simply a linear shape. It's just two atoms bound together with a covalent bond. And the bond angle is 180 degrees. Okay, so this shape really just matches the same way we drew it in Chapter 8. 9.5, we have CH, Cl3. All right, carbon in column 4, 4 valence electrons, hydrogen, 1 valence electron. Chlorine is in column 7, so 3 valence electrons. All right, so carbon like that, each hydrogen like that, each chlorine, 2, 3, 4, 5, 6, 7. So each chlorine just has one open slot. The hydrogen just has one open slot. Carbon would go in the center. So this is a central atom surrounded by 4 single bonds. Okay, if we were to draw this like Chapter 8, it would be something like this. I won't draw the dots. So 3 chlorines and then a hydrogen. So if you have a central atom with 4 single bonds, then that is a tetrahedral shape. Okay, so the way that we draw that is with carbon in the center. All right, it doesn't matter if you pick hydrogen or chlorine, but we'll go ahead and just put hydrogen on top by itself. We need to draw one thick line for chlorine, and then one dashed line to signify that it's in the back. Let's go ahead and draw the other valence electrons. Okay, so 2, 4, 6, 8. 8 for each chlorine, and hydrogen has 2. So this is a tetrahedron or tetrahedral, whichever you prefer. And the bond angle for the tetrahedral shape is 109 degrees. All right, we'll go to, just turn the page and we will go to 9.6. 9.6, we have arsenic trichloride. Okay, well, arsenic trichloride, so that'd be AsCl3. Okay, so let's find arsenic. Arsenic is in column 5. So it would have 5 valence electrons, a non-metal. All right, and each chlorine, we've drawn chlorine many times over there in column 7. All right, so we have 3 chlorines. Each chlorine can only take a single bond, right, because it has that one open slot. Arsenic would be in the center. Okay, so if I were to draw it like Chapter 8, it'd be something like this. I'm not going to draw the dots. This is just a premature draw here. That's like Chapter 8. Well, if you have, and I'll go ahead and draw that pair that's right here for arsenic. So if you have 3 single bonds surrounded by a central atom, that's a pyramidal shape. Okay, so the way that we draw that, we'll draw arsenic here in the center, a chlorine, and a chlorine. We do have that lone electron pair left. All right, of course, each chlorine has 8. So this is a pyramidal shape. And the bond angle for pyramidal is 107 degrees. All right, so the answer that we're looking for is that, okay? This was just to show you what it looked like before we went through the molecular geometry process. All right, 9.7, as we move along, we're going with sulfur dibromide. So sulfur dibromide, if you remember from chapter 3, would be S and then Br2, sulfur dibromide. Okay, sulfur in column 6, like oxygen. Looks like that. Each bromine is in column 7. All right, so bromine can only take a single bond because it only has one open slot. Right? But we have 2 bromines. So we would have sulfur in the center. Now the chapter 8 version of this would be like this, right? Not going to draw the dots again. If we have a central atom surrounded by 2 single bonds, okay, that is just like water, right? It's going to be the bench shape. So that looks like this. So it's bent, and the bond angle is 105 degrees. All right, and I'm so sorry. Let me, I forgot the dots on that. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Don't forget the dots on your test. All right, and then we'll put those 2 pairs up here, and they're influencing that shape and squishing down those bromines to 105 degrees. Okay, so all right, that is 9.7. Let's do 9.8. All right, for this one we have SiCl2O. All right, so silicon would be the central atom because it has only 4 valence electrons, has the most unpaired. Each chlorine, as you know, because we've drawn it so many times, has 7 in column 7. Then oxygen is in column 6, so 6 valence electrons. Okay, silicon, we have 2 chlorines. Each chlorine can only have a single bond. Just has one open slot there. Okay, so if silicon goes in the center, so let's do it like we did in chapter 8 real quick. You'd have 2 of your chlorines, not going to draw, and then the other 2 dots here, other 2 electrons, could bond a double bond with oxygen. Okay, so what shape do we have that has a central atom, 1 double bond, 2 single bonds? That is trigonal or trigonal planar. Okay, so the double bond with the oxygen, single bond with the 2 chlorines. All right, so the way that we show that, we'll put silicon in the center, and it's kind of like the spokes of a wheel. We'll put a chlorine there, an oxygen there. Let's get the dots. Make sure silicon needs 8, right? 2, 4, 6, 8. Oxygen needs 8, 2, 4, 6, 8. Chlorine needs 8, 2, 4, 6, 8. Both of those. So this is trigonal. And the bond angle for trigonal, you just have to memorize this, 120 degrees. All right, so that does it for page 4 on your notes. Flip over to page 5. So here we'll talk about a purely covalent bond. And we are on page 298 in the book. We've moved over to 298. So a purely Purely covalent bond is a bond where electrons are shared equally. So we're going to talk a lot about electronegativity. So for example, with Cl2, right, that's going to be a linear shape that looks like that. Since it's the same atom, all right, the same atom, they both have the same electronegativity or tug on another atom's electrons. So the tug of war over those electrons cancels out. Okay? So we call that a purely covalent bond. All right? When the tug of war cancels out, we're even Steven. Now you can also have a polar covalent bond. The example in the notes is H2O. So here, let's go ahead and draw the shape. We drew this on yesterday's lecture. It's the bent shape. Okay, so looking at the periodic table, what has a greater electronegativity? Oxygen way over here or hydrogen way over here? Well, electronegativity, the highest is up here in the corner with fluorine. So as you go up and over to the right, the electronegativity or tug on other atoms' electrons, desire for other atoms' electrons, increases. So oxygen has a way higher electronegativity than hydrogen over here. The way we show that is we put an arrow on the bond. Oxygen is winning the tug of war. Okay? And the book even puts a little straight line, but you've got an arrowhead going toward the more electronegative atom. Well, what that means is that oxygen will develop a partially, what that Greek symbol means, I believe it's delta, a partially negative charge, and each hydrogen, because it's losing some of that electron, will develop a partially positive charge. So if we were in class, I could show you what I usually do with the students is I blow up a balloon and I rub that balloon on my hair, okay? And a bunch of electrons will come off of my hair onto the balloon. Okay, we talk about that phenomenon in physics. So the balloon becomes very negatively charged. Well, what happens, I put that balloon next to a stream of water from the sink, and the water will literally pull over towards the balloon. Instead of coming down out of the sink in a straight line, the water will pull towards the balloon. And the reason is because the hydrogens that are partially positive are attracted. So there's a water molecule on its side. They're attracted to the negative charges. So it causes the water, okay, let's say this were the sink, all right. So we've got a tap here, all right. The water would be coming out and literally curve over towards the balloon because the balloon has a bunch of negative charges on it. And I demonstrate that every year in class, and my hair looks crazy after doing it. Okay, so that's all described in this verbiage right here in the notes. And so let me draw a few more examples of polar covalent bonds. I've left you space in your notes to draw these. So the first is NH3. Now we drew NH3 yesterday on the notes, and what we found out was that it had a pyramidal shape. So we got our thick line there. So if I were to show the polar bonds, okay, which one is more electronegative? Nitrogen or hydrogen? Well, nitrogen's further to the right than hydrogen, so it's more electronegative. So we just show the arrows pointing towards nitrogen. The book puts that flat spot behind. I don't care so much about that as I care a lot more about those arrowheads showing which atom is more electronegative. C2F4. So if we were to draw C2F4, okay, if you were to go through the process, we would have a double bond with carbon and then 2 fluorines attached to each carbon. All right, and we'll go ahead and put the electrons. Because fluorine has 1 open slot, so it can accept a single bond. Well, how do we draw the polar bonds? Well, fluorine is the most electronegative atom on the periodic table. Okay, so fluorine is really, it's the king of electronegativity. So everything else loses out to fluorine, and certainly carbon does. So the way we show the polar bonds would be with the arrows pointing towards fluorine. All right, let's look at on your own 9.9. All right, so we are, turn in your book to page 303. All right, we're at the bottom of page 5 in your notes. So it says identify and label the polar bonds. So the first one is CO2. Okay, CO2, carbon is in the center. We've drawn this one before. You'd have a double bond with each oxygen. Right, this is that, and it has a linear shape. So who wins the electronegativity tug of war? Oxygen or carbon? Well, here's oxygen. Here's carbon. All right, you tell me. All right, someone says oxygen, and they are right. Okay, it's further too. So let's show that arrow like that. Show the arrow like that. Okay, the book does this kind of thing. Again, don't care that much about that. I want to see the arrowhead. All right, B, CClF3. Okay, so this is fluorines in column 7, chlorines in column 7. They can both only take single bonds. This shape would be a central atom surrounded by 4 single bonds. So what shape is that while I'm drawing? All right, that is the tetrahedron shape. And we know chlorine wins the electronegativity battle with carbon because it is to the right of carbon on the periodic table. So chlorine is down here. Even though it's down 1, it does win the battle against carbon. Fluorine wins the battle against everyone. Okay, so that shows the polar bonds for CClF3. All right, just a little more to go today. If you'll look at the top of page 6, we're going to draw 3 more examples of polar and purely covalent bonds. Okay, so for example, let's say we have CF4. So again, on your notes, we're at the top of page 6. Let's go ahead and draw that. So that's going to be carbon with 4 single bonds, so a tetrahedral shape. Okay, we know, we've already talked about it, that fluorine always wins that electronegativity battle. But this is actually, even though this has polar bonds in it, we say that this is a purely covalent molecule overall, because those fluorines all have an even tug. Okay, so since the pull on the fluorines, the pull on the central atom is the same, they cancel each other out. So this is written in your notes. Since it's an even tug all the way around, think of it as will the carbon move? No, it's an even tug all the way around. Fluorine's all the same. Carbon won't move, so it's purely covalent. All right, let's try the next one on the notes. I think I can fit it down here. PF3. I believe we've already drawn PF3, or certainly one like that. We would have phosphorus in the middle. You know, fluorine will only accept single bonds. Okay, that phosphorus needs that lone electron pair. Okay, who wins? The fluorine wins the electronegativity battle. Always does. Okay, but if you'll think about this, whereas we had a fluorine up on top that was canceling out the movement of the other fluorines that were kind of pulling down into the side, right? These fluorines are all just pulling down. The fluorines, so the phosphorus will move down, if you want to think of it that way. So if the molecule will move, then it is polar covalent. Why that's important, I'll tell you with tomorrow's lecture. Okay, but if you'll read the text in the notes, this molecule will have a net downward pull, therefore it will develop a charge and be polar covalent. So polar just means electrical charge. Purely no electrical charge. Polar has an electrical charge. It would conduct electricity if dissolved in water. Okay, one more and then we'll stop. So we have CFCl3. Okay, carbon always in the center, right? 3 single bonds. Now it doesn't really matter where I draw the chlorines and where I draw the fluorines. It would still give us the same answer. I'll draw the chlorines down and the fluorine up, though. Okay, doink, doink, doink. Okay, remember column 7, 2, 4, 6, 8. 2, 4, 6, 8. Gotta have 8, right? Okay, fluorine is more electronegative than chlorine. Okay, so the poles aren't going to cancel out. All right, let me draw those polar bonds in there because fluorine and chlorine have different electronegativities. So remember, these are kind of pulling mostly to the side, a little bit down, but mostly to the side. Fluorine's going to win. This molecule will move upward. Well, if the tugs, if those bonds don't cancel out, it's polar. So it has to completely cancel out to be purely covalent. So what that means is that this molecule will have an electrical charge to it. So it will conduct electricity when dissolved in water. Okay, and that explanation is given there right in the notes. Definitely worth reading through. Okay, here are the rules. We're going to start here tomorrow with the rules to determine if a molecule is polar covalent. We'll start there and work some on-your-own problems that have to do with whether something is polar or purely covalent. Okay, the homework that goes with this lecture. All right, well, you did review questions on the last homework. You did 1 through 6, I believe. So let's go ahead and do review questions on page 317. You can go ahead and do 7 and 8. Go ahead and do that. And we can do practice problems on page 318. You did 1 through 3 last time. Let's go ahead and do 4 through 8. So this lecture took much longer than it will take you to do this homework. But you really need to understand it. You need to be able to draw those shapes. All right. Rewatch yesterday's lecture again. Rewatch lecture number 1 if you need to. You need to be able to draw those shapes. Look at the periodic table and determine which atoms are more electronegative. Remember, top right corner, most electronegative. Lower left corner from chapter 8, the least electronegative. As you go up and to the right, more electronegative. Okay, so at the end of chapter 9, chapter 9 has one more lecture, I will do a solutions video, and you will definitely want to watch that and make sure you did all the homework correctly. I will talk to you next lecture.